All right, we have seen in the last video about an electric field, which we have said is a way to mathematically represent the influence of a single charge on the space surrounding that charge. It looks like this. Well, mathematical representation is good. I mean, it's a physics class for goodness sake. But we also sometimes find it handy to represent things graphically. So we have some conventions to draw in an electric field, sort of draw an electric field. An electric field exists everywhere in space, so we can't draw that, but we can draw some representations that will help us understand what the field is doing. To do that, we're going to have to follow some conventions. And so let me give you a source charge. I'm going to write this, I'm going to draw this as a little circle because I need to leave the space around it free of any letters, so I'm going to put the Q there. This is a positive source charge, and I'm going to assume that this charge is isolated. That is, it's so far away from any other charge that it, for all practical purposes, feels no influence, right? Okay, so the electric field in that case is going to be represented like this. And I'm going to be as careful as I can to draw everything nice and symmetrical. Now, that works just fine. Notice these look like vectors. The electric field is a vector field. A field line is what we're going to call these. You should think of it as made up of lots and lots and lots and lots of little vectors. I'm saying that now because at some point we're going to see these fields start to curve if I bring in other charges. We know that vectors can't curve. So this is should think of these lines as representative of a lot of little vectors. They're not vectors themselves, but they are representative of little vectors, right? So what I've done is I've drawn this symmetrically. And notice that these lines are pointing away. That is one of our conventions, which I'll write down. Field lines point away from positive charges. In fact, why don't I write it down now? Field lines point, make sure this is in frame, good, away from positive charges towards negative charges. I'll draw a negative charge in just a second. So if this charge is just sitting here, there's no reason to think that it affects space differently up here than it does down here, or over here than it does here. That's important. The word we're dealing with is isotropy, or isotropy, depending on how I've heard it said both ways, which is just a fancy physics word for meaning that the influence of this thing is symmetrical. That's important because what I did not draw was this. If I were to draw that, just looking at this, this looks to me like the field is stronger up here than it is down here. And in point of fact, that is what that would mean. Second point here, density of lines indicates field strength. Just barely. So if I were to draw it like this, there's a greater density of field lines up here, which would tell you that the field is stronger up here. There's no possible reason to think that one charge would be asymmetrical like that. And so if I drew this, that would be incorrect. I would need to draw other ones. And notice I am being careful to be symmetrical. Right? Should I stop there? Well, that kind of depends. Graphically, it might be a good idea to stop here, but I don't have to. Remember, this is a representation of something that exists everywhere in space. And so when I look at this, you just have to know that this is a representative sampling of the field lines. I could continue on, but if I do that, right, I've got to keep it symmetrical. That's kind of symmetrical. I could continue on, right? But it's going to get really convoluted really quickly. So I'm not going to. And in fact, I would probably never draw this many field lines if I were to be drawing a field. But I'm just showing you as an example. I would probably stop with the 8 field lines that I had before I, doubled it here. But that's the idea. I'm just representing the fact that this is an influence on the space. Now, it's never, or I should say, it's not always incorrect to draw more field lines in one region than the other. If you have some sort of strange charge distribution, like if you have an insulator and you put a lot of charge in one region and a little charge in another region, then yeah, you're going to have a stronger field in one region. But for this case, it wouldn't make any sense to draw this asymmetrically, right? So that is a positive charge. Let's talk a little bit more about this, the density of field lines. If I were to draw, let me get a different color here. If I were to draw, say, some sort of oval shape right there, and then I'm going to do my darndest to draw the same size oval right here. Notice that the density of field lines in this oval, or the amount of field lines passing through this surface, might be a better way to say it, is less than the field lines passing through this surface. I did my best to draw these about the same size, which means that the density of field lines in this surface is bigger than it is here. What number 2 says is that means the field is stronger here than it is here. But that makes sense because we know that there's a distance dependence, right? The closer I am to the charge, the stronger the field is. The farther away I am from the charge, the weaker the field is. And if I were to draw that, even further out, like say here, then I would only have one field line going through it. And that would mean the field was even weaker. So that actually is a nice little bonus from just drawing it correctly. This distance dependence becomes obvious because the density of the field lines indicates field strength. Good. All right. Now, let me say that this is in one region of space and in another region of space way far away from this one, so there's no influence felt between them. I'm going to place a negative charge. The field from this will look very similar to this one. I'm just going to draw the 8, not the 16. So there's 4, there's 8. Right. The difference is field lines point away from positive charges and towards negative charges, so my direction is now flipped. Right. No big deal. They're still in straight lines. Right. I'm going to say this now and draw it in just a second. That's because the stipulation I made that this is far away from any other charges, no other influence being felt here. All right. So 3 lines, and when I write lines, I mean field lines. I just don't want to write the word field all the time. Lines end on negative charges or at infinity. That means infinitely far away. So for this case, the lines end on negative charges. Up here, we don't see a negative charge. We're going to assume that these just kind of go off to infinity. Right? I could draw this the other way. Lines start, write it the other way. Start on positive charges or at infinity, right? Which is what's happening here. We're going to assume that they're starting infinitely far away. Now, be careful. This is a rule for drawing. We know that if there's a field, there has to be a charge somewhere. So when I write end at infinity, what I mean is that they end on a negative charge, which is so far away that we don't even care about it. It's not affecting our system. Same thing here. These are emanating from a positive charge somewhere, but it's so far away that we don't really care about it. That's another way to think about it. We've always got to match up the physical reality with our mathematical idealisms, right? So, okay, that's what I'll say about that. Okay, so this is a single charge. What happens now when I put charges together in close proximity? So I should point out there are much better graphics than I'm going to be able to draw here in your textbook or easily searchable online. I'm going to do my best, but I'm not an artist and I don't have computer-generated graphics available to me just to type a button and hit. So I'm going to do my best, but you can find better pictures of this. Let's take a single charge plus Q and another charge minus Q. We're going to assume that the magnitudes of these charges are the same, but their signs are opposite. Okay, so how will I draw the field lines here? Let's look at the single positive charge. As long as I stay really close to this positive charge, I should expect the negative charge to not have much influence. Remember, distance dependence. And so if I'm really close to the positive charge, I would expect my field to look something like this. Same over here. If I'm really close to the negative charge, I should expect my field to look something like this. So if I draw the field lines really close, and I'll draw in the direction in just a second, I'll draw in the arrows. But if I stick really close to my charge, I expect it to just look like an isolated charge. Same thing over here. But remember, a field represents influence. It represents the influence on the space of the charges. And so if I'm somewhere around here where I'm equidistant from both charges, I'm going to be feeling an influence from both charges. If I put another charge up here, it's going to feel a force. If it's a positive charge, it's going to feel a repulsive force from here, an attractive force from here. And so if I'm trying to represent the influence of these charges, I'm going to have to allow my field lines to curve and show that. So as I get farther away from the positive charge, the negative charge starts to have an effect. Let's examine this field line right here and see what that might look like. As I move away from the positive charge, I'm going to have to do this kind of without seeing it, sorry. I'm actually going to come around to the other side so I can see what I'm drawing. As this thing gets farther away from the charge, I expect the negative charge to start to have more and more influence. And it might look something like that. Now, let me draw in the direction and make sure this satisfies the rules I've developed. Away from positive charges toward negative charges. Starts on positive charge, ends on negative charge. That seems like it satisfies my rules pretty well. And with that in mind, I can probably just do the others with just by making them look pretty similar. Right? Of course, there's going to be one here that just goes straight on in. Good. Now what about this one? Well, this is probably going to do something like this. And this is probably going to do something, I'm going to go off the page, like this. And this one will wrap around like this, and so on, and so forth. Of course, if I'm at the extreme edge over here, I'm going to get one that just, if I'm on the same line of action with the line connecting these two, this one will just go on out for, oh, I'm sorry, that comes in. Yeah, this one goes out. But every other field line except for these two right on that line are going to exhibit this curving nature. And I think I do that okay, but you might have seen this before. Probably you've seen a shape very similar to this in 5th or 6th grade science, where either your teacher showed you a picture, or if your school had the resources, they took a bar magnet, put it down, put a sheet of paper on top of it, and sprinkled some iron filings on top. Those iron filings arranged themselves along a shape that looked very similar to this. That was a magnetic field. This is an electrical field, but actually there's a really interesting connection between those two, which we will explore as we get farther and farther into this course. For now, what I want you to know is that this particular field between a negative charge and a positive charge of the same magnitude, this field between plus Q and negative Q, reminder, this is the condition we're satisfying. The magnitude of the charge is the same. Is called an electric dipole. Di meaning two, and pole meaning one of these things, right? We call this a pole. This is an electric monopole. That's just a fancy word for the one charge. If I put two of them together in this particular arrangement, that's called a dipole. You can have a quadrupole, a hexapole, whatever. But this particular one is called a dipole. It turns out to be really, really important if you go on to study more physics in later classes. For now, I just want you to be familiar with the term. This is an electric dipole. So that's the charge existing between a positive charge and a negative charge. Let's look at one more. What about if I actually, let's look at a couple more. What about, can't talk. What about if I bring in, or if I have a positive charge and I bring in another positive charge? So I've got two positive charges. Okay, same assumptions, close to the charge. They're gonna look like they do from a single isolated charge. That is to say, the other charge is not influencing very much this space really close to this charge. This one's dominating. But as they get farther and farther away, right, I will start to feel the influence of the other charge. In this case, though, the field line is not going to curve toward this charge because this is positive and this is positive. I have a repulsive force if I put a positive charge in here. So the field line showing influence is going to do something like this. And, you know, right off the axis is going to do something like this. There might be one that comes out here. And so on and so forth. And let's just continue this. I'm on a roll. That's good. Yeah, so this would be the field that you would get between two positive charges of equal magnitude. The same would be the case for negative charges, although the arrows would be reversed. And so, again, your better graphics to look at. This is really just to get a feel for what these things look like. So, yeah, hopefully that makes some sense. One other example I want to look at. What happens when I have two charges of different magnitude? Let's do this. Plus 2q minus q, right? So this is positive, this is negative, but this charge by magnitude is exactly twice as large. All right, fair enough. Well, what I'm going to draw here, let me do the same thing I've been doing. Well, I know that this one's going to just come right over here and connect, no big deal. This one's probably going to connect. This one's probably going to connect. Now, after that, I might have left myself in a pickle with the number of lines I've drawn. And this one's going to go from far away. Now, if I'm going to accurately represent these charges, what I'm going to have to do is I'm going to have to let there be more field lines coming from this one than there are from this one, right? Why is that? Well, if density of field lines represents strength of field, this one is producing a larger field. It's a bigger charge. So I'm going to represent that by having not 8, but 16 lines come off of this one. And yeah, I'm not going to be able to do this very well, but that's okay. Let's see what I got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We need a few more. This is not going to be very symmetrical. It's okay. I never claimed to be an artist. And what I'm going to have to do is let some of these lines connect, right? That's 5, 6, 7. And that's okay. I should have another one connecting. This looks horrible. My apologies. Again, better graphics online. I've destroyed my symmetry a little bit. That's okay. The point is, if this is my situation, and these of course will continue on out. They won't connect though, because I'm only going to allow it to connect a certain amount because of the difference in the charges. the upshot of this is, if I didn't know that this was plus 2q, I didn't know that this was negative q, I could determine that just by counting the field lines. How many are coming out of here? 8. How many are coming out of here? 16. That tells me immediately that this charge is twice as much as this. And then I could notice that they are connecting. That tells me this is negative and this is positive. So if you didn't know this information, you could actually still get it just from this graph. Your graph would look much better than this. Is a terrible looking graph. My apologies for the graphics, but that's the idea. If you're given this situation and you say, well, what's the ratio of this charge to this charge? You count the field lines, 16 field lines coming out of this, 8 field lines coming out of that. The ratio of the charges is 16 to 8 or 2 to 1, or the ratio from here to here is 1/2, either way you want to do it. What sign is this charge? Well, you look at the arrow, the direction of the arrows. Positive. What sign is this charge? Look at the direction of the arrows. Negative. That's how that works. All right, so this is an easy way to represent things that usually take a little while to write mathematically, but it's a nice shorthand to give us a way to visualize it. All right.